Students, myself Alok Kumar Pandey, Assistant Professor, Electrical and Electronics Engineering Department, Kite Group of Institutions. Today I am going to tell you the experiment whose objective is the step response of first order and second order system for different gain with the help of linear system simulator. Before going to the practical implementation of this experiment, I am going to brief something which we have already studied in the theory classes. So here I am considering a system whose order is first order, that is 1 by st plus 1. So transfer function of this system Cs by Rs is equal to 1 by st plus 1. So if we cross multiply in this equation, then Cs is equal to Rs into 1 by st plus 1. If we are taking input is impulse input, then Rs is equal to 1, as we studied in the theory classes. Impulse is Laplace of impulse input is equal to 1. So Cs is equal to 1 into 1 by st plus 1, that is 1 by st plus 1. To get the response, time response of this first order system, we need to take the inverse Laplace of this equation, that is Ct. The inverse Laplace of Cs is equal to Ct, and the inverse Laplace of this term will be 1 by t into e to the power t small t divided by capital T. Here capital T is time constant, right? So input, here we have taken impulse input. Now if we are taking step input, so ut is equal to 1 for t greater than or equal to 0, and if we are using a square input rt like this and passing a system whose transfer function is just k by s, you will see it in on the kit, then integration of this square wave will get a ramp signal like this. So integration of rt dt from t is equal to 0 to t is equal to t, we will see it like this. So now we will see, as I said earlier, if we are applying a square wave input to an integrator k by s, where k is gain, then we are getting a ramp output. So we will see it in this kit, where only two kits are there. This one is a digital oscilloscope on which we will see the output of the system, and this is the linear system simulator in which all the necessary arrangement regarding the control system will be available. Like this is the disturbance input, this is the reference input, this is the feedback path, and this is the gain. And here integrator block is there. So if we want to add one integrator block, then we will use this. If we want another integrator block, then we can use this. And we can add the time constant with this block. So with the help of these two kits, we will able to see when a square wave is applying to an integrator, how can we get a ramp. See that a square wave signal is connected to the system with ground, and we can easily see on the digital oscilloscope that a square wave is entering. So as I said, in last time we have connected only square input. Now I have connected an integrator out of it, integrator with this. So we will pass this square input to this integrator, right? And we are providing a reference input here. Reference input, that is square wave. So square wave as a reference input, and we are passing it with this integrator. So as I said earlier, if we pass a square wave with the integrator, we will get the ramp input. Now we can easily see here on the digital oscilloscope that output of a square wave with integrator, ramp output we can easily get on the digital oscilloscope, as we have mentioned in this book. In previous section we have applied a square wave to a first order system. Now we want to see the response of a second order system with this square wave. So here this GS is a first order, but if we will take a feedback, then it will be converted in a second order system. So if we provide a RS input, then output of the system will be underdamped output, as I studied in the theory lectures. Previously we have not connected this feedback. We have connected both these points, but we have not connected this feedback as well as this time constant, extra time constant. So with the help of these two connections, now we have prepared this system of a second order system, and we are applying again a square wave to this second order system. Now we can easily see underdamped output we are getting at every switching area. I mean, whenever output is switching from higher to lower, then this transient behavior it is showing in the graph, in the oscilloscope, and it is damping out as time approaches towards infinite. So this is a behavior of an underdamped system in which oscillation of the system is reducing with respect to time. So this is the actual behavior of a second order system with a square wave input under the value of zeta, where zeta is between 0 to 1. So that we can easily identify with the transfer function of the second order system, so that we have already studied in our theory classes. So now today what we have studied, we have tried to see the response of a first order and a second order system with the help of this linear system simulator and digital oscilloscope, in which we have found that if we apply a square wave input to an integrator, then we can get a ramp output, and if we are applying a square wave input with a feedback system, closed loop first order system, then it will convert to the second order system, and the output of the system will be underdamped system that we can easily see in the digital oscilloscope. Thank you so much.